Hi, I'm David. My mentors at AutonLab are Professor Artur Dubravsky and Dr. Nicolas Gisolfi, and over the course of the summer, we research interpretability of large language models. So, language models are pretty dominant these days, not only in natural language processing, but also in computer vision and robotics as decision transformers. But their architecture remains a black box model, which is particularly important when it comes to their limitations, such as generating incorrect information and knowledge hallucinations. And it brings us to a concern. What kind of representations has the model learned? We'd like to know this to apply them in impactful domains, but also to fix them. So, how can we address this problem? The standard approach is behavioral evaluation. So basically, getting at that dataset, benchmarking it, comparing it to different models, and seeing how well it scores against them. But ultimately, you would like to know what is really going on in the internal representation of language models. And just benchmarking is not enough. Traditional software has reverse engineering tools like IDA or Ghidra, so what about neural networks? There's really nothing like this in deep learning space. But the interpretability field could actually give us and help us reverse engineer neural networks. There's this loose analogy between computer programs and reverse engineering them and applying mechanistic interpretability to neural networks. So a program binary is basically network weights, and virtual machine is a network's architecture, and memory and variables are activations and neurons inside neural network. So over the summer, I surveyed a lot of interpretability methods to search for components of such a debugger. So probing is one approach, which is basically training a classifier on layer activations, or unsupervised probing, such as contrast consistent search, which searches for layers that are consistently calibrated when it comes to their uncertainty on a given binary label facts inside their datasets. Or inference time interventions, which searches for patterns of activations inside particular layers that consistently predict either a truthful or a false output. So, other approaches try to find key value memories. So, for example, the ROAM method tries to find where the model knows the Eiffel Tower is by prompting it with the Eiffel Tower is in, and trying to figure out what it knows and where this knowledge is stored. This can actually help in editing such a memory. It relies on causal tracing, and in interpretability research, there are different methods like activation patching and path patching, which are actually different names for a very similar method, which basically is about ablating certain activations. So basically substituting these activations with different values, like zeroing out or taking a mean and in distribution training samples, and trying to find direct and indirect effect of such substitutions on correct predictions. There are methods like automated circuit discovery, which can automate this entire process of searching by applying different graph traversing methods on a computational graph of the architecture of the transformer. And Tracer, a laboratory for interpretability, which is a really good way for unit testing these automated circuit discovery algorithms, because we can compile simple programs directly into transformer weights. Two ways of interpretability which I want to highlight are logit lens and adversarial attacks. So the first one is basically a layer-by-layer approach where we take a decoder's probabilistic outputs that are linear transformations of the final layer and apply this intuition to transforming all of the intermediate layers of activations. And this results in the internal representation of the model that we can visualize as a changing distribution over the vocabulary on each layer, which is particularly important for debugging if we want to see if the model converges very quickly in its layer depth to a final output distribution. Adversarial attacks are pretty good because they can target undesirable behavior, and we can test in what kind of circumstances, on what kind of input sequences the model outputs such undesirable behaviors. And there are optimization techniques that find such prompts. When it comes to filling research gaps, our contributions are the survey paper, opening up the Pandora's box on debugging large language models, where I talk about these previous methods in more detail, and I try to lay out the main components of the hypothetical debugger for large language models. But also our contribution is in combining prompt optimization in adversarial attacks with this layer-by-layer analysis in the vocabulary space to find layers that contribute to an unintended behavior. And we believe that this should unveil if current safety approaches, such as reinforcement learning from human feedback, can adequately align the entire model or just a part of it, leaving backdoors for vulnerabilities like prompt injections. And our evaluation is ongoing, meaning we take our algorithm and test it on NeurIPS 2023 Trojan Detection Challenge, which is about finding hidden backdoors inside language models. And we specifically try to search for text inputs that succeed in outputting a harmful behavior. So I would like to take a minute and give special thanks to RYS's coordinators, Rachel Bursin and Dr. John Dolan, as well as my mentors, Professor Artur Dubravsky and Dr. Nicholas Gisolfi. Thank you.